Hello children, welcome to channel Sube. Today I am going to discuss question number 44 from MCQ part of 2019 Physics New Syllabus paper. Each of the single turn wire loops placed on XY plane as shown in the figures. That means we can make a loop winding a coil. Coil means a certain wire, copper wire, insulated, having an insulated coating, so that is called coil. So like this we can wind and make a frame like that. But in this question they say that the frame has only one turn like this, only one turn like this. So that is the meaning of that single turn wire loops placed on XY plane as shown in the figure. Carries the same current I. So it carries the same current I in each loops. A uniform magnetic field is applied along the positive direction of the x-axis. A uniform magnetic field like this is applied like this everywhere, covering the total loop like this, but I draw only one line for convenience. The direction is towards positive direction of x-axis like this. So there are number of lines like this, the field. How do they do it? How do we do it? If we happen to apply a magnetic field, children, we need two magnets like this. You know, bar magnets are there, N, S, and sometimes you can buy from a hardware shop, because they sell the small magnets for cupboards, the doors, cupboard doors. We call pantry cupboard. So they sell in hardware shops. Small magnets are fixed to the door so that it stick to the frame without locks. You can keep the frame, you can keep the door closed. So we can buy at low prices. So you have to place one magnet here, say the polarity S, another magnet here, say the polarity is N. So N to S, the lines are going N to S, so therefore you have to place N pole here, S pole here. So usually if you buy a magnet, or if you have a magnet, it has both poles, but like this you have to place S pole closer to this side and N pole away. So at left side you have to place N pole closer and S pole away, far away from this side. So then N to S, N pole and S pole are closer to each other, therefore they are acting. N to S force lines are there. Force lines will be created in this field, in this atmosphere, in this surrounding. So that is how we do it. So however, they have what they say, applied along the positive direction of the x-axis. Now let's go to the question. Assume that each wire loop can rotate freely about its symmetric axis perpendicular to the magnetic field. Perpendicular to the magnetic field. Magnetic field is this way, perpendicular direction is this way, perpendicular to the magnetic field. Which choice represents the order of loops that the initial torque acting on them are in descending order. Descending, that means we have to write the largest one first. So some students might not understand what this stories, therefore I have to explain a little bit. So let us suppose this is the frame, loop, that they say loop. So to make a loop, first of all you need a frame. They don't say that in this question, just they say wire loops. Just you can't make loops using wires because they bend here and there. You can't keep it stable. Therefore, first of all, you have to make a certain frame using wood or plastic or some soft material. Using some soft material, you have to make a frame like this, and then you have to make a small groove along the sides of this frame like this. This one is the frame, like this. This one is the frame. So actually, when I was in school, in A-level classes, I made a thing like this, and I made a galvanometer even. So therefore I can understand at first glance when they say this story in such a question. So I used an eraser, just an eraser that we used to erase whatever we write on papers using pencils, the eraser, because that is very super soft. So I penetrated, I sent a sieving needle, sieving needle, the machine, from the machine I can remove it. There is a needle, sieving machine needle. So I sent it at the middle, exactly at the middle like this, so that it appears from other side like this. So the point is here. So this can now rotate like this, clockwise or anti-clockwise. So to make sure it rotates well, so I placed an eyelet at the bottom like this. Placed an eyelet, eyelets that I used to use in our clothes, eyelets like this. Small hole there, small dip there. So the eyelet I placed, so the needle tip is placed there without moving here and there properly. So I stuck it to a piece of wood properly so that not move it, and I put another eyelet here on top of this sieving needle like this, the eyelet here. So that also I fixed to a frame made of wood like this. So now this eraser can be rotated very easily because no friction here and there. Easily this eraser can be rotated clockwise, anti-clockwise. So then we can wind the coil around this. There is a groove, so the coil also is stable, it doesn't move here and there. Properly we can wind this and take the ends like this to the needle, and we can apply some glue to fix furthermore so that not move, to ensure the loops don't move here and there. So like that, if you have done activities like that, easily understand, you can easily understand the question, because these people who make these questions have done those things. So sometimes they don't write all the words because they assume that students know these things. So this is the story about this frame, how it can be rotated, and how this axle, we say axle to that sieving needle that I said that I fixed here at the middle, this needle. So it is the axle, that is the technical word that we say, axle. So we make a certain simple axle so that it can be rotated. So freely it can spin around that axle. If we fixed an axle like this at the center like this, and friction should be very low. That is why I used two eyelets at the top and bottom. So those things they don't say in this question. So that is how really we make it. So that is why each wire loop can rotate freely about its symmetric axis. That means we have to fix that axle exactly at the middle, so that the parts would be symmetric axis, perpendicular to them. So that is how the story. So now let's try to solve this question. I have to redraw this frame a little bit larger because I have to write a lot of things inside this. There's no enough room. So imagine that the loop is this one. So the current they have shown like this, I. So you must know the current along this side is opposite like this current flow. So the B, that means field, magnetic field, is applied like this according to the question, to the direction of positive of x-axis, positive side of the x-axis like this. So this one we denote by B, the symbol is B, is the magnetic field strength or magnetic field intensity. So you have to find out what torque. In this question what they ask is initial torque. Torque means the force times the perpendicular distance. Torque we denote it by tau. Tau equals F times D. So we have to find out F. First of all, F. So there is a force here, because there will be a force here, because there is a magnetic field and a current both. If there is a magnetic field and a current, this current is given by a battery. That also you should know. If you confuse everything, you can't get the correct answer. So the current flows this way, then the positive of battery must be like this and negative this way. So like this we give a current, because in generators we don't give a current, we rotate by mechanical power using our hands or wind or water. In generators, there you have to apply right hand rule, and here you have to apply left hand rule. That is why I am explaining. If you get confused all things, you will not understand. In generators we don't give a current. The current is given by the generator, so we receive current. But here, so in generators what we have to give? Mechanical power. We give mechanical power and we get current I. Here we give current to the loop and we get mechanical power, that means force. So that should be clear. Here we use left hand rule, Fleming's left hand rule. So since there is a magnetic field and since there is a current, both should be there, and length also. Usually the length is there because the wire is there, and not only the wire, there must be a field along the wire. Field must be there, spread all over the wire or a certain length. Say this length, that is enough. Somehow there should be a length where the field is available hooked with this conductor. It should be hooked. Hooked means penetrate. If the magnetic field is somewhere else, like this, magnetic field is somewhere else, the conductor is somewhere else, like this. So we can't get such a force then. That is why we say the hooked flux. That is important. That means the field lines must go through this wire. So that is how we have to assume, because the question is given like that. So now we have to find torque. So I said torque is equal to F times D. So a force is given by this current and this field. So developed here, appear here, since there is a B and I value. But they should be perpendicular to each other. You know, I am going to use this pictures. So that is what we call left hand rule. So when we place our this finger, index finger, what we call index finger, when we place the index finger in the direction of B, field strength, to the direction of B, and we have to then turn without change in this direction, that already we have pointed towards B, our index finger, then this center finger, middle finger, but here we say center finger because center finger current, that's how we keep in our mind, so that we won't forget it. Center finger current, normally we say middle finger, but here we say center finger current. We are given the direction of current is, we are given the direction of current is towards this way. So we have to rotate our hand so that keeping this one constant, so that this center finger direct points towards the direction of the current. So now we have to look at the thumb. The thumb is directed to this way, that means towards the paper, towards this screen. So there will be a force towards the paper, means we draw an arrow, so we see when the arrow is directed to towards the paper, just we see the back of the arrow. So there are feather, that is why we draw a cross like this. So this is the method we denoted the direction of force. The force is towards the paper, this according to this method, this rule, force. When we locate our hand, fingers, index finger to B, towards B, center finger towards current, because we know already the direction of current and direction of B. So then we have to see the direction of thumb, that gives us the direction of force. So that way we can find the direction of force is this way. So the same way we have to find the direction of force in the other part of the loop. So we use the same hand, left hand. I must write it, otherwise you might get confused. Left hand, not right hand. We use right hand in generators. This one is not generator. This is a motor. This is a motor, not a generator. We give current and we receive rotation or force. So we have to place our left hand like this, the same way, so that our index finger is towards B. We know B already, and center finger towards current center finger. We know already the direction of current, so we have to place those two fingers. And now look at the thumb. Thumb is this one. Thumb is coming out from the paper. Therefore, we draw a dot. That means the tip of the arrow. The tip of the arrow. So, like this, we draw a tip point, like this. That is the point of the arrow. This is the back of the arrow. So now we know the direction of force. This one is the force. So everywhere like this, along this wire, force is acting. Along this wire, force is acting towards the paper like this, into the paper along this wire. So that is it. So now let us draw the diagram again. When we look at it from top view, from top, when we look at it like this, from the top, how do we see? We see this wire, and below this wire is this one, so we don't see this one. Just we see these wires like circles like this, from the top. That is how we see. So from the top, we see the top wire like this. Top wire means, I use a color, purple color. This wire we see like that, and that is all we see. We don't see the wire below it because it is covered by this one. And then we see, we don't see actually. We have to cut it, the other wire, the vertical two wires like this. That we don't see actually, we see like this. So the force, this force line and this force line we see, because we now already have discussed that into the paper, this one out of the paper like this. So from top we can see this one like this, this one like this, equal forces. The magnitude of this force is given by, you must have learned the equation, F equals B times I times L. L means the length where this B is experienced by this wire, L. So that is L. So now let's look at this wire. What is the force acting on this wire? You can see the magnetic field intensity B and I are parallel to each other. Therefore, no force is there, because according to this rule, I and B must be perpendicular to each other. So there's no so there's no force acting on this wire. and the same thing happens here. There's no force acting on this wire as well. So therefore only these two we have to consider. So now we are going to find out the torque, because in the question they want us to find out the torque. Torque is F times 1F. There are two F's, but remember in the equation the definition of torque is 1F times the distance, the perpendicular distance. Perpendicular distance is this one, say d. You have to remember this one, only 1F, one force. Since there are two, we take only 1F. So when you write this equation, you must always say that 1F, 1F, one force. Otherwise you will confuse, you will forget, and you might use both F's in future when you use this equation. So therefore remember 1F. So F we know, VIL, then distance, let us mark here that this distance, it is d. So now we have a term like this, L times d. What is L times d? L is the length of this side and d is the length of this side. So when we multiply that two, what we get? It is equal to area of the loop. These two give us area. So torque equals BI times area of the loop. A is area of the, remember, of the loop, not wire. The area of the wire is the cross-sectional area. When you cut the wire like this, area of the wire is this one. So there is a very small, tiny one. That is not in this equation. Capital A is the area of the loop. That means this area. It is a certain big value. So now we have received capital A in this equation. So B is constant everywhere, I is constant. So we can write tau is proportional to capital A. So we have to find out the maximum tau and the minimum tau and other values in between them. So instead of that, we can find out, we can compare capital A area. So that's what we have to do now. If the capital A area is larger, then the torque also larger. So let us first try to find the area of this loop. What is the height of this loop? From 1 to 5, then 4. Then here from 1 to 2, then 1 times 4, then 4 is the area. We don't know the units, they have given just 1, 2, 3, 4. So here we get 4, area equals 4. Then this one, 1.5, 1 to 2, and then from 2 and 3 in between, that means 1.5. Here also 1.5. Then 1.5 times 1.5. Then 2.25. That is the area. Here then there are two triangles. Let's find out the area of one triangle. So this side 1, the height is 1 to 4, that means 3. Then 3 times 1. We don't have to multiply it by half because there are 2. Then 3 times 1, total area is 3. Total area is 3. So here the radius is 1.5. 1.5. So 5r is squared. The area is 5. The exact value is 3.14. Let us use just 3. Then r is squared. R is 1.5 squared. Then 3 times 2.25. 3 times 2 is 6. 3 times 25 is 75. 6.75. So now we have finished all the areas calculated. So this one is the biggest one. So that means the letter R. R should be at the beginning. So these two. Then the smallest is this one, 2.25. That means S. S at last. S at last is here. This one P. So this one is the answer. Second one is the answer. So children, I think you can understand the way I solve this problem. So there is another way that is shorter, but you should remember the equation that tau equals VINA. So I will explain it now. So children, now let us go to the second method, that is shorter. Second method, that is shorter. You must have learned the lesson galvanometer. So galvanometer has a same type of loop, same type of loop, the same type of axle, and same type of magnetic field like this. So there in galvanometer the equation you come across is tau equals VINA. So in that galvanometer lesson we learn N equals the number of turns. So here in this question there is a single turn. So then N equals 1. Then tau equals VIA. N equals 1. So the same way, B constant, I constant, tau is proportional to A. So we have to check only area. So the same way as we previously did, we can find out the maximum area and the minimum area and select this answer as the correct one. So children, I think you can understand. If you are happy, please subscribe my channel. See you tomorrow, not at 8 o'clock. I have decided to upload videos at 6 o'clock, so you can watch my videos from 6 o'clock. So watch my videos again and again. See you tomorrow. Thank you for watching my videos. Goodbye.